Yes, hello there. My name is Macklin Leah Bialy from Group 15, and we are presenting a single model architecture for scalp pathology detection. So under this, we are looking at the introduction, the related work, problem statement, all these, the references, and also the acknowledgement. So under our project, we looked at trichology, which trichology is a branch of dermatology focusing on hair and scalp health plus the diagnosis. So we see that worldwide, many millions of people are being affected by scalp conditions. But again, assessment being done manually is subjective, inconsistent, and also time consuming. So with that gap, we came in to address it through modern revolution. So this involves the use of image data sets plus machine learning. And in the end, we get results which are standardized, objective, scalable, and accurate. So our main goal was to get objective, standardized, scalable, and scalable trichological assessment. So in the related works, we've seen that convolutional neural networks can detect hair-related diseases with greater consistency than manual inspection. So that's why the CNN-based approaches have been applied to detect common scalp conditions like dandruff, folliculitis, as we shall be seeing in our project. So looking at the domain application problem in our context, we say that hair and scalp disorders are widespread and often diagnosed through manual inspection, which we've said that it is time-consuming, it is subjective, and it is also a slow process. So that becomes a domain problem. So in the computational context, we see that the problem we are having is not just building a model, but we are having a problem that we have to build a trustworthy pipeline from the point when we are having raw data to the point where we are having a full system which we can use to be able to do the scalp condition detections. So these are the questions we considered during our research. We considered the role the environmental stressors have in the hair health. So here we had a question which links biological factors with the trichology and external environment variables. So we also had another question whereby we had to ask ourselves, how do the external environmental factors in our data set correlate with observable scalp and hair alterations? Then the other question was, how effective are current diagnostic imaging techniques combined with the machine learning workflows? So all those questions were considered as we are carrying out our research. So the research objectives were exploring and pre-processing scalp image data sets, also evaluating the proposed semi-supervised framework against fully supervised baselines, and assessing the clinical applicability of the developed models. So in our research objectives, we aimed at understanding our data set through the pre-processing. We also aimed at building the frameworks, and that is where we had to build our models. Then also understanding which solutions can be able to be used during the problems we are having. So these are the research contributions which we got. We developed a new supervised learning approach specifically for spotting the scalp conditions earlier. So we also built a model that brings together information from the actual images of the scalp and microbiome data from the scalp environment. Then we had to create 20 clean, easy to understand visualizations, which will be explained in the later slides. So this is the data description. We saw that we used the imaging data, of course, which imaging data has high resolution scalp images labeled for conditions such as alopecia, the folliculitis, psoriasis, dandruff, and also dermatitis. So can take on through the next slides.
Hello, so I'm Onyanga Ambrose. I'm going to be taking us through the visualizations. So these visualizations are for output results. First, we have to see the classes that are in the AirScalp that analysis access. Yes. So here there are 8 different classes. Yeah, you can see alopecia areata, all those ones. Dry hair, folliculitis, gray hair, head lice, psoriasis. All those are the classes. And then the number of annotations per class. It means that, for instance, alopecia areata had 277 annotations. And then contact dermatitis had those numbers, and the rest are also like that. So those are the ones that are available in the annotations. So thirdly, we have this pie chart, and it's helping us to visualize the shares of the total annotations. Here we see green, the dandruff has the most. It has the most annotation if you see it with the portion that it takes in the pie chart, followed by, let's say, contact dermatitis. And then this other side, uh, whereas the pie chart and the rest of the things we have been seeing, what looking at annotations, these other ones are going to show us exactly how many images uh, are contained. So in train, there are 722 images, then valid, we have 86, then test, we have 78. Next slide. So in this other, we want to see the class distribution across splits. So in all these splits, you see that for orange, the train has the most data in all of them. So it means that you see for alopecia areata, train is still the tallest, followed by test, then the valid. Same with all the rest. Just that we can see very well that dandruff had the most values at a time, but looking at the different classes, still you will see that test is the second, and then followed by valid. Apart from, let's say, for folliculitis, you see that the test is less than the valid. And then looking at the Pareto chart, mostly looking at the line, specifically the line, shows you that first, uh, if you say cumulative annotation coverage, for the cumulative means that they keep adding. So if you consider dandruff alone, it will be the images of the dandruff only, the annotations of dandruff. That's why it starts small. But when you add folliculitis, since it's cumulative, they will add them to the dandruff too. That's why the line keeps increasing until they reach the end. Yes. And then this other one, we see average bounding box width and height per class. Yes. Now, bounding box is, for instance, if you look at the head of a person, if the person has maybe head lice, a bounding box shows directly which part of that head. It puts a box around the part of the head that has the disease. So the average means um, the average width of each of the, uh, for instance, average width of alopecia areata, the average width is represented in blue. So it would be around 260 there. I'm assuming around that. Then this other one is maybe 275 for the height. Then it has given us for all of them. Yes. So let's go to the next slide. For this, we are looking at the visualization of output results in terms of bounding box area per class. So it means that uh, in this box plot, it's showing us the area per bounding. So let's look at psoriasis. You see that in this one, the upper boundary is the most, above 200,000 square pixels. So it means that psoriasis has the largest bounding box. For instance, if the head of a person maybe has psoriasis, it would be having a bigger a bigger area of a box. You get it? So it means it will be affecting a bigger patch of the head. So the ones which are small, like dandruff, shows that the bounding box is small. That means it affects a very small portion of the head. Now, the rest, like folliculitis, they have average, like small. There's no problem with it. But in this box plot, you see those other circles on top of the boxes. It shows the outliers. So much as the most fit within a certain thing. You look at folliculitis, much as most are within purple, with the line showing the average, the top of the box showing the upper percentile, then the lower one is showing the lower percentile. The others up show the ones which are like outliers. So most of them are down, but there are some outliers. And then for bounding box, for this other for let's wait. I'm trying to remove the picture so that shows me. So for this other bounding box center heat map, first we have to understand that the relative x and y shows exactly the center. Yeah. So that means uh, if you see down is relative x, then sideways up is relative y. So it means that most of the annotations appear at the center of the image. Yes. So you can see the heading is saying where annotations sit inside the image, and since the darker part of the heat map is towards the center, it means most of most of the annotations exist around the center of the picture, with the most being at 40 around the top. Yes. So next slide. Our next discussant can take over. That's past Pauline Mbasani.
Thank you so much, Ambrose. My name is Pauline Peace Mbasani, and I'm going to be taking you through the next part. We are going to start with the discussion. Previous slide, please. At this stage, after analyzing the data, the focus is on preparing everything for building the model. This includes cleaning the data, making sure labels are consistent, and organizing the data set properly so it can be used smoothly throughout the next stages. Then finally, we run a few test trials to make sure everything is working correctly before moving on to the full model development. Next is the conclusion. To conclude, this project shows that using semi-supervised learning can really improve how we detect scalp conditions. By combining image data, environmental factors, and biological information, we're able to get more accurate and reliable results. Overall, this approach helps move trichology from manual and inconsistent diagnosis to a more standardized and data-driven method. Then I'm also going to look at the limitations. However,
Previous slide. Okay.
previous slide, sorry. There are some limitations that we consider while working on this project. First, there are not enough labeled images, which makes training more challenging. Then some conditions appear more than others in the dataset. Like Ambrose explained in the visualization, we had dandruff appearing more than psoriasis, so that's one of the limitations we are facing. Then lastly, the system is still mainly for research and needs real-world clinical testing before full adaptation. So for now, we are using the system, what we have developed so far, for research, and we've not yet deployed it into the real world. So for the next steps of our project, we look at fully preparing the dataset and finalizing with pre-processing. Then we shall run more tests and improve the model to make it more accurate and reliable. Eventually, the goal is to develop a system that can be used in real clinical settings to support diagnosis. Then finally, we acknowledge some of the resources we used in our project and in our research. Thank you so much. That is group 15.
SW